Hello guys, my name is Barnam Parashar and I am a student of Assam Don Bosco University studying engineering in the Department of Electronics and Communication. I have made this video today to discuss something about Cmos. So let's start. What is Cmos? It is a very effective logic circuit and can be established by constructing a P-channel and an N-channel MOSFET on the same substrate as shown in this figure. We have an induced P-channel on the right and an induced N-channel on the left. This configuration is referred to as complementary MOSFET arrangements or CMOS. This configuration has a lot of advantages which we are going to discuss in the upcoming slides and has resulted in a whole new discipline known as CMOS logic design. So let's see something about CMOS logic design. Implementation of various logics using CMOS. One of the very effective use of complementary arrangement is an inverter as shown in this figure. It consists of an NMOS transistor and a PMOS transistor. The input is connected to both the devices and the output is at the drain of both the devices. The positive supply voltage is connected to the source and the PMOS transistor, and the source of the NMOS transistor is grounded. Here this transistor is the NMOS transistor and this transistor is the PMOS transistor. So let's see how it operates. When we apply an input of 0 volt, we get VGS equals to -5 volt and VGS1 equals to 0 volt. So the PMOS transistor is on and the NMOS transistor is off. So we get an output voltage of 5 volt. So we see when we apply a 0 volt, we get an output of 5 volt. Again, when we apply an input of plus 5 volt, VGS2 becomes 0 volt and VGS1 becomes plus 5 volt. So the PMOS transistor is off and the NMOS transistor is on. Thus we get an output of 0 volt. Thus we see that when we apply a 0 volt input, we get 5 volt output, and when we apply a 5 volt input, we get a 0 volt input output. So this circuit acts as an inverter. Let's move on to NAND gate. So how to design a NAND gate? This figure shows a CMOS 2-input NAND gate. Here Q1 and Q2 are parallel connected PMOS transistors and Q3 and Q4 are series connected NMOS transistors. When A equals to 0 volt and B equals to 0 volt, that is, we apply an input of 0 0, VGS1 and VGS2 becomes -5 volt and VGS3 and VGS4 becomes 0 volt. So Q1 and Q2 becomes on and Q3 and Q4 becomes off. So we get an output of 5 volt. So again, when we apply an input of A of 0 volt and B of 5 volt, that is a logic of 0 and 1, we get VGS1 equals to -5 volt, VGS2 of 0 volt, VGS3 of 0 volt and VGS4 of plus 5 volt. So we get Q1 as on, Q3 as off, Q2 as off and Q4 as on. Thus V out becomes plus 5 volt. Again, when A is 5 volt and B is 0 volt, we get a VGS1 of 0 volt and VGS2 of -5 volt, VGS3 of 5 volt and VGS4 of 0 volt. So Q1 is off, Q3 is on, Q2 is on and Q4 is off. Thus we get an output of 5 volt. Similarly, when we apply an input of both high inputs, that is A and B are both set as plus 5 volt, we get that Q1 is off, Q3 is on, Q2 is off and Q4 is on. Thus we get an output of 0 volt. So let's see the truth table and the discussions that we already made. So we see that when A and B are both low, we get an output high. When either of A and B are high, we get an output high. And when both A and B are high, we get an output of 0 volt. So we see this is the truth table of NAND gate, and so this is the circuit of NAND gate using CMOS logic. Let's move on to NOR gate. So this is the 2-input CMOS NOR gate. Here NMOS transistors Q3 and Q4 are connected in parallel and PMOS transistors Q1 and Q2 are connected in series. So when seeing the truth table, we can see that when A and B are both low, Q1 and Q2 becomes on and Q3 and Q4 becomes off. So we get a V output of 5 volt. And again, when we apply A and B, that is different outputs, we get output voltage low. And again, when both the inputs are high, we get an output voltage which is low. Thus we see that it is the truth table of a NOR gate. Thus this circuit behaves as a NOR gate, and so this is the design of NOR gate using CMOS transistor. So let's see the comparisons between the various logic families. So here in the first column we see the names of various logic families. TTL stands for transistor logic, ECL stands for emitter coupled logic, MOS stands for metal oxide semiconductor logic, CMOS is the one we are discussing, and IIL or I2L is the integrated injection logic. The second column is basically the switching speed, where we see ECL and IIL is the fastest and CMOS not quite so fast. The third column we see power dissipation, which is a very important criteria, where CMOS has the least value. This is a very important advantage of CMOS. The fourth column discusses about noise margin. It is the amount of noise that a circuit could withstand without compromising the operation of the circuit. Here also CMOS has an advantage with the noise margin of 10 volt, which is higher than the other logic families. The fifth and sixth column discusses about fan in and fan out. Fan in of a logic gate is the number of inputs that a logic gate is designed to handle. Fan out, also called loading factor of a logic gate, is defined as the maximum number of standard loads that the output of the gate can derive without impairing its normal operation. So and again, so on the final column we see that the cost comparison of the various logic families. So let's realize, so after discussion of all these slides, let's make a quick roundup of why it is good to select CMOS. First of all, low power consumption, which is a very important criteria which works in favor of CMOS. Then in CMOS it has always a high input impedance, so it draws almost zero current from the driving gate, and therefore its fan out is very high. Also we can see that the high noise margin, it means that a signal which is logic 1 with finite noise added to it is still recognized as logic 1 and not logic 0. In both low and high states, noise margin of CMOS remains the same, which is 30% of VDD. So in noisy environments, a higher VDD is preferred. So we get a better noise immunity. So we can say that CMOS gates are very simple, and together with the low power consumption, it makes for dense integration. That is, we can incorporate more transistors in the same size of IC. So we get a very good value for the cost and power and the size. This is the reason why CMOS logic design is very useful in VLSI system designs. Hope you learned a little bit about CMOS from this video tutorial. Thank you and have a nice day.